Hello students, this video is for hydraulic engineering on Friday the 31st of January. As I previously mentioned, I'm down in Greenville, South Carolina today working on questions for the FE exam. So we're going to have this recorded video which comes from a previous semester. Of course the underlying material is the same, but I do want to give you some updated announcements. So homework number 3, which is related to 3 reservoirs, is due on Wednesday, February 5th. That should be uploaded to Blackboard before class on Wednesday. And so now today what we're going to be doing is another 3 reservoirs situation, but this time instead of using the Hayes-Williams equation for estimating friction loss, we're going to move forward with Darcy Weisbach, which is more accurate but a little bit more complicated. So in order to enable that, I'm also going to talk about the fully turbulent flow assumption, which is a way for us to do better than just starting with a strict guess on the F value and kind of infer from other circumstances what a good starting estimate would be. So if you do have any questions on the material or the assignment as you're working through it, please feel free to send me an email or you can contact me on Teams, and I'll be back in my office on Monday. So otherwise, I'll see you in person again on Monday. And let me know if you've got any questions.
Now, just to revisit this ongoing dilemma that has popped up already twice before, the tricky thing about the Darcy Weisbach equation is we know it's accurate, but that accuracy comes for a reason, and it comes at a cost. The reason why it's accurate is because the F value adjusts to the actual flow conditions. The F value isn't just always some factor that depends on the materials, but it also depends on the pipe diameter and the flow conditions. So then if the F value depends on flow conditions and flow conditions depend on the F value, then we can't know at the outset what F value should be used in any problem where the flow rate's unknown. Now sometimes the flow rate is given. You know, there will be problems both in this class and in the real world where, you know, the flow rate Q is just some given at the outset of the problem, and then you can avoid this dilemma. But this dilemma applies in situations, for example, where there isn't a pump, where there's a free flow condition, where we don't know what the flow rate's necessarily going to be at first between 2 reservoirs, or from a reservoir to a free discharge of a pipe. So Reynolds number depends on velocity. Velocity depends on friction factor, which depends on Reynolds number, and so on. So what do we do? Well, what we've done so far is we've just started with a guess of the F value. And we can do better than that. That's what the fully turbulent flow assumption says is, you know, you could just start with some uneducated guess for the F value, or you can get a little bit closer to the mark by looking at part of the Jane equation, or looking at part of what influences the F value. Even if you don't know all of the factors that influence the F value, you know some of them at the outset of a problem. So the fully turbulent flow assumption is that let's just say that what if the flow rate was really high? So there's a big velocity. Well, what then? If the velocity is high, then that means that the Reynolds number will be big. So think about down in the denominator of the Jane equation, inside of this logarithm function, we have 2 terms. One of the terms depends on the relative roughness. The other depends on the flow conditions. And if the Reynolds number is really high because the velocity is large, then that means that this second term becomes insignificant compared to the relative roughness. So in other words, if Reynolds number is big, then this term goes to 0, or effectively 0, if it's very large. And then we could calculate the F value just by looking at 1.325 K sub S 3.7 times D. We just pretend like the second term is not even there if conditions are fully turbulent. So fully turbulent is the phrase that we use to describe really high velocity. And it's not like unrealistically high. Sometimes conditions are fully turbulent. And what that means, when the conditions are fully turbulent, it means that the F value is no longer affected by any further increases in velocity. And if we look at the Moody diagram, there's a section of the Moody diagram where the F value is affected by both a change in Reynolds number and the relative roughness. But then once we get past this dashed line, we notice that the curves are flattening out. Like, they were pretty steep at first, but they're flattening out considerably. And so what that means is, if you've got a Reynolds number of 10 to the 6th and a relative roughness of 0.004. So for a relative roughness of 0.004, you could have a Reynolds number of 10 to the 6th or a Reynolds number of 10 to the 7th, and the F value is about the same. Or it could be 2 times 10 to the 7th or 3 times 10 to the 7th, and we're still on this horizontal portion of the curve, which means that the F value doesn't change when we get to the right of this curve. So rough turbulent zone, otherwise known as fully turbulent flow, is just a way for us to begin with a better guess for the F value than just picking something at random or just choosing a midpoint value. And it allows our solutions to converge more quickly. And that's less important now when we're doing a lot of the calculations with Excel. But if you were taking this class 10 years ago, I had the students do some of these problems by hand, iteration. And in cases like that, you wanted the solution to converge as quickly as possible, because every additional round of calculations was going to take a good 15, 20 minutes. So it's still good for us to apply the fully turbulent flow assumption, and we'll use it in future classes as well, but it'll be a part of the example we work through today, rather than just starting with some typical F value. So let's revisit the 3 reservoir problem, kind of what we know classically, what we're trying to find out. We'll be given some water surface elevations in reservoirs, and we're wanting to know the flow rate through each pipe. And then if we know the flow rate through each pipe, then that would allow us to determine the pressure at the junction, which may also be something we're interested in. So the approach that we applied in class on Wednesday was, we said we know the water flows from the highest reservoir towards the junction, and from the junction to the lowest reservoir, but it's that middle reservoir we're not exactly sure about. And the flow depends on the amount of energy at the junction, and that is determined by the head loss through each pipe. So there's this general rule that water flows from locations of high energy to locations of low energy, and it's not necessarily the physical elevation at junction D that affects how much energy is there, because it's the pressure at junction D that most of the head is located at, the head that'll be driving flow. So our process that we go through is calculating the head loss through each pipe based on some guess of what head there might be at D. And then we apply the continuity equation, because what we know is that the flow has to be conserved through this junction. Any flow that goes into the junction has to go out. And so if the water is going from A to D, then that would mean QBD plus QAD is equal to QDC. Flow in equals flow out. We don't know the magnitudes, but we can start with a guess, and then by checking continuity to see if there's balance between the inflow and the outflow, that tells us how our guess has to be adjusted. And then we keep iterating until the solution reaches convergence. And convergence has 2 criteria. It means that the flow in and the flow out are equal, and then also that the friction factors have stabilized and aren't changing anymore. That didn't apply on Wednesday because we were using static friction factors with the Hazen-Williams equation. But today we're going to use the more accurate approach. Darcy Weisbach equation will give us a more realistic estimation of the head loss through each pipe, because it's going to reflect the flow conditions. And so today's solution will be more complicated, but it's more reliable and accurate. but we have to look at two criteria for convergence. It's the flow rate balance and convergence of friction factors F. So just to summarize the method that's implied by the spreadsheet template that you've got, we're going to be looking at the head loss through each pipe. And so we could say that the head at D, for example, is the head at A minus the losses through that pipe. That's how much energy there is at D. We could say that the amount of energy at D in terms of the head at C is the head at C plus the losses. Now think about the flow direction. Why is it minus for one of these and plus for the other? If the water is flowing from A to D, then that means we know there's going to be losses in the direction of flow. So there will be less energy at D than there was at A. So that's why we're subtracting the head losses for this first equation. And then if we relate the head at D in terms of the head at C, we're adding the head loss. So plus H sub F, because if you're going against the direction of flow to get from reservoir C to junction D, that means that there has to be more energy at D than there was at C. These are the equations that will apply in this process, and we'll start with a guess of how much head there is at D. And we'll find the amount of head loss in terms of what the velocity is and the F values. And we'll have to start with some simplified guess for F in the first iteration, but subsequent iterations we'll calculate it based on the full Jane equation. And then we'll recalculate what the velocity would be based on the F values. And we will compute the Reynolds number. With that, have an improved F value, an improved velocity. And then we look at the flow balance by Q equals VA through the pipe, and then checking to see if the flow in and the flow out are equal. If the flow out of the junction is too large, so think about what that means. If the flow out is too large, then that means that our guess for the energy at D was too high. Like if we say there's a lot of energy at D, then that's going to force a lot of flow through DC, but then there will be very little flow through AD and BD if our guess of how much energy there is too high. If the flow out is less than the flow in, then that means we need to raise the guess of how much energy there is at D. And when in is and out are equal, then assuming that the F values have converged, then we're done and we've got the solution to the problem. So any questions about the fundamentals or the method that we're applying, or how things are different now that we're using Darcy Weisbach instead of Hayes and Williams? All right, well, if not, what I'd like you to do is open up that spreadsheet template, because we're going to apply it to this scenario where we've got water at 120 feet in reservoir B, at 100 feet in reservoir A, and 70 feet at reservoir C. So we want to know the flow through each pipe and the pressure at D. And in order to determine the pressure at D, we have to know its elevation. If I remember the homework correctly, the first homework problem, I don't tell you the elevation at D, or at the junction. I don't tell you the elevation of the junction, but I'm also not asking for the pressure at the junction, I think, in that problem. I think maybe, if I remember correctly, the first problem, all you have to do is find the flow rates. And you can do that without knowing the elevation of the junction. You don't necessarily need to know the elevation at the junction unless you're calculating the pressure. So we're going to go through this process. You'll note that I give you the kinematic viscosity of water, 1.22 times 10 to the minus fifth feet squared per second. We've got the material properties of the pipes and their diameters, their lengths. All right, so let's look at this template file. Here it is. So does everybody have these same elevations on the diagram of 120, 170? Yeah? I changed the template file a little bit compared to previous years, and I just want to make sure I didn't accidentally give you the old version of the template file. All right. Well, looks like this time we've already got the initial data for the pipe defined, so we don't have to type that in. We've got cast iron, and galvanized iron as our materials. The lengths are given. The diameters are defined. The cross-sectional area, remember, is pi d squared divided by 4. So our first thing that we have to do is just guess what is the head at D. Now, there's no right answer for what should the initial guess be. We could guess 95, we could guess 101. Just for purposes of illustration, let's start with a guess of 90 feet, because there's something I want to show you. If we start with a guess of 90 feet, then we'll have to go through a certain step that you may encounter later. And if we guessed something else, we may not go through that step. Okay, so I'm going to base these other rows just based on that 1 so that I could change the 1 and then it would update all of them. But I want it to be 90 to start with. The first time we're determining the head loss through the pipe, this is where we're doing subtraction from the reservoir water elevation to our guess for how much head there is at D. So we're starting with pipe AD. So if it's 90 feet of head at D and the water is at 100, then that's implying that the water is flowing from reservoir A to the junction. So let me just rearrange this arrow just so that we can keep in our minds the flow direction that is implied by this head. So I'm saying that there's a head of 90 at D. If there's 90 feet of head there, then the water would go from A to D. So what that means is the head loss would be 100 minus our guess of 90 feet of head. So that's saying that there's 10 feet of head loss through the pipe if there was 90 feet at junction D. BD would be equals 120 minus the head at D. And then DC would be our 90 feet of head minus the elevation of 70. So equals 90 minus, oh, actually, I could just click on that location. 90 minus 70. Okay, so our head losses are 10 feet of head is implied through AD, 30 feet through BD, and 20 feet through DC. Okay, so any questions so far? Does anybody need me to take a look at the spreadsheet or answer any questions? All right, now here it's saying let's assume fully turbulent flow. Instead of just saying 0.02, let's try and do better than that by taking, here's the full Jane equation. So when we're assuming fully turbulent flow, I'm just going to type in the Jane equation, but I'm going to ignore this second term in the denominator. So it's equals 1.325 divided by the parentheses logarithm ln of K sub s. Now check, is K sub s in units of feet? Yes, then the diameter should also be units of feet. So we'll just check to make sure that's true, and we didn't type it in as inches. Looks like we're okay. So 1.325 divided by the logarithm of K sub s divided by 3.7 divided by D, and then close parentheses, and then that entire denominator is squared. So the squared term needs to be outside of the logarithm. So we're squaring it after it's done the logarithm function on K sub s divided by 3.7d. So this is what the F value would be if the flow rate's pretty high. If we have a big velocity, then the F value should be 0.0208. That's just estimating the F value based on the relative roughness. And relative roughness is K sub s divided by D. Relative roughness is weighted in the Jane equation with 3.7 in the denominator, but relative roughness is just how rough the pipe is in terms of equivalent sand roughness to the pipe diameter. Okay, now I've typed in the fully turbulent flow assumption here. It's just referring to the K sub S and D, so I can drag that down through the other rows in this iteration. And it's interesting to see that we don't have the same F value for each of these pipes because they have different K values, they've got different diameters. So that's good. We've got a slightly better F value than we otherwise would have. Now the velocity is going to be estimated based on rearranging the Darcy Weisbach equation. We have an F value that's estimated. We know the pipe lengths, that's given. The diameter is known. The H sub F is dependent on however much head there is at D. So the H sub F that goes into this is the H sub F that's implied by our guess of the head at D. So let's type in this equation. V equals SQRT of H sub F times D times 2 times G. And remember, I made this mistake last time. If we're in traditional units, G is 32.2. Okay, and then we need to divide it by F. Now this equation is centered, so I can't click on cell I-27, but I can type it in. I-27 times the length. Okay, close the parentheses in the denominator, close parentheses for the end of the square root function. I wish there was some way for me to make it bigger, but it's probably tricky to see. But you've got the equation itself. If we've typed that in correctly, then we should see a velocity of 5.24 feet per second. And we can drag that down through the other two rows. So it's estimating the velocity through AD would be 5.24 feet per second, the velocity through BD 10.1, DC 9.68. Okay, any questions or concerns so far? Okay, Reynolds number is just velocity times diameter divided by kinematic viscosity. So equals this velocity times the known diameter divided by the kinematic viscosity in terms of feet squared per second. So I'll just type in 1.22 E minus 5. Okay, so we've got a Reynolds number here. Now why are we bothering to calculate the Reynolds number? It's because we want to have an improved guess for the F value. Remember this F value, the first one we calculated, it's only based on the relative roughness. And I mean, it's a good start, but we can do better because we've got velocities now. So we want to incorporate the velocity into the full Jane equation. So here where it says F updated, now instead of just using the fully turbulent flow assumption, in the next step, here in step 6, we're going to use the full Jane equation to calculate the F values. So equals 1.325 divided by parentheses ln parentheses of K sub S, just clicking on the cell location, divided by 3.7 divided by D plus 5.74, 5.74 divided by, now the Reynolds number, that is in cell K27, and that's to the power of 0.9. Now I close the parentheses around the logarithm, close parentheses in the denominator, and square everything. I think I can make this bigger. Let's see. Oh, but it'll only be it as I'm typing it in. Well, let's look at how different is our f value now. It didn't change a lot. It changed a little. It went from 0.0208 to 0.0218. So maybe like 6% or something. It changed a little. Okay, we can drag down through the other two rows, and it'll calculate an updated value for f.
Click on your equation there one more time.
Mm-hmm. Can you actually see that? I don't have a sense for how tiny that is from the back of the room. You need to start bringing a telescope to class, I think, if you're going to sit back here. You can kind of make it out. Okay. Anybody got questions? We're not in too big of a rush. I've budgeted plenty of time for this example, so if you do have a question, feel free. So yeah, we're going to calculate the velocity again. Same way we did last time. It's just that now with this calculation of velocity, we're using a better f value than we did before. Okay, so we're typing in the rearranged Darcy Weisbach equation. So it is h sub f times d times 2 times g, which is 32.2, divided by f using the new f value, so that's L27, times the length, and then all of that is to the power of 0.5. Or I could have done SQRT at the beginning, to the 0.5 power. So the first time around, my guess of the velocity was 5.24. Now I know with a little bit more accuracy that it's 5.12. You can drag it down and find the velocity through the other pipes. Now we have to label what is an inflow and what is an outflow. It's because we're going to be calculating the flow balance here in just a minute. So with the H value that I assumed at D, then water is coming into the junction from pipe AD. If the head at D is 90, then water's flowing from A to D. So water's coming into the junction from that pipe. So I'm going to say in, because it's coming into the junction from the pipe in question. BD is also in, because if the head at D is 90, then water's going to go flow from 120 to 90. So that means that the flow direction is from B towards D. That's also an in. And then this last one is an out, because if the head at D is 90, it's going to go from 90 to 70. It's going to flow out of the junction towards reservoir C. So these are the labels that we apply. And then the flow rate, Q equals VA. We've got the V right here and the A over there. So Q equals velocity times the area, and we've got a flow rate. So we can calculate the flow rate for each of the three pipes, and now we just want to look at, is it in balance, or do we have to make some adjustment? So we want to find out out minus in. So the outflow is this one, and let's subtract both of the inflows. So it's minus this inflow and minus the other inflow. So it's however much outflow minus however much inflow. And since it's negative, what that means is that there's too much inflow. So let's look at this little reminder at the top here. It says, if out is bigger than in, then the guess of HD is too high. So in our case, it's actually the reverse of that. In is bigger than out. So that means, let me write the conclusion here. Since in is bigger than out, then our initial guess of HD is too low. So I had guessed 90, so that tells us it's too low. Now we can tinker around with our guess and just see what happens. Like here, this, remember, was the one cell that everything kind of is dynamically updated based on. Let me make it a really light yellow. All right, I can play around with this, and let's keep an eye on how does that affect the indicator of flow balance. All right, so what if I said 91? If I change it from 90 to 91, do we get closer to being in balance? Yeah, 92, closer. 93, closer. What about 98? Closer. 99, okay. What about 99.99? Closer. Now, why am I like being delicate here around 100? Well, remember that this elevation is 100. So if I said, well, what if it's 101? All of a sudden I've got an error. Does anybody know why I've got an error when I switch to 101 feet? Well, the flow direction is going to change. If, as it now seems likely, because let's see, 99.99, it was still, the guess at D is still too low when it's 99.99. So probably that means that how much head is there at D? There's more than 100 feet. So for me to do that, I'm going to have to change a few things structurally in my solution, because if the head at D is more than 100, then that changes this flow direction to be into the reservoir rather than out of the reservoir. So that's why this, I can't just say like do one goal seek and find the, let this be 0 and find the head loss, the head at D that causes it. It would never find a solution because of this crossover point. So if I do 101, doesn't work. So let me just do like 99, and then I'm going to create a new iteration. This new iteration is going to have updated F values, and I'm also going to fix the issue that was causing that error, like the direction issue. So all of the pipe characteristics are the same as they were before, but now let's start with the guess of let's do 110, because we know it's more than 100. How much more? Not sure yet. Let's make it 110 for this next iteration. Okay, so make it all refer to the previous cell above it. Okay, head loss through the pipe. It is going to be, for AD, it is 110 minus 100. Okay, BD would be 120 minus whatever we've got at the head at D. And then if it is at 110, then it'll be 110 minus 70. So this minus 70. Okay, so if the elevation of the water of the head at D is 110, then that tells us, yeah, I've done something, let's see.
So are we changing the direction of the...
Yeah, we are. We're going to change what's in and what's out. Yeah, so see the arrow here, like the direction that the arrow is pointing is just maybe for us to be able to see it and think about it more easily. But yeah, if the head at D is 110, then that means the water's going to go from D to A. Yeah. So the head loss is like from B towards D, and then from D towards A. But it's 10 feet of head through pipe AD, 10 feet of head through BD, and like maybe you'd be able to see it easier if we said 111. Then it's 11 feet of head through this one, 9 through that one, and 41. All right, so the F value, we can just use the previous iteration, like these values here. So I'm going to say equals and just click on the previous row for pipe AD. So it is the previously calculated F value. And now let's calculate a new velocity. Rather than typing in the equation again, let's just copy the formula in a relative basis. If you click on these cells, well, if you select them and then you copy, I like to do that by Control C, and then paste down below it, Control V. What it pastes is the formula. It doesn't paste the values, it pastes the formula. And so it's going to calculate the new velocities without us having to type in the formula another time. And we can do the same thing here with the Reynolds numbers, where we don't have to type in the equation for Reynolds number. I can just highlight the Reynolds numbers and then copy them, and down here paste. And what it pastes isn't the number, it pastes the equation, and then it calculates the result of the equation, and that's what we see. So then the same thing for the updated F value. I can just select the cells and paste them. Calculates a new F value. And by the way, how much is the F value changing? 0.0234, 0.0219. It's still changing a little bit. So like one of the convergence criteria that we're going to look for is not only is continuity satisfied, but how much is the F value changing within the iteration? And it hasn't completely stabilized yet. That's all right. It's just an indicator that we're going to have to do more iterations after this one. Okay, the velocities again we can calculate, we can copy and paste, and it calculates the new velocity. Why are they so different? Well, the head losses are pretty different than the previous iteration. If you've got a higher head loss, then that's going to increase the velocity through that pipe correspondingly. Now, what's an in and what's an out? We have to kind of reason through this again. So if the head is at 110, then the flow is into the junction from BD, but it's out of the junction from pipe DA. So this AD is out, BD is in, and DC is out. Any questions about that? Like why we say in versus out? Everybody have it? All right, the flow rates, remember, it's just the velocity times the area. So we could either type in the formula or we could just copy from the previous iteration. Control C, Control V. And let's calculate the out minus the in. So the out is this out plus that out. So now we've got the combined outs, and subtract the in. Okay, it's not 0. 0 would mean we have no error. So let's see, if Q out is greater than Q in, then the guess of H sub D is too high. So since Q out is larger than Q in, that means our guess of HD was too high. Okay. We could do goal seek a little bit here. Like, see how it was 110? Well, does 109 get us closer? Yeah. 108. 107. We could try data, what if analysis, goal seek, and we can run goal seek so that this error is 0 by changing the guess head value. And it'll get us pretty close to the solution. Like, there's no error in the in versus the out, but we're not done yet because the F values are still changing a little bit. And if you look at the velocities are still changing a little bit. So let's do iteration 3. Let's make our guess 104.665 as our guess. And then we can copy all of this stuff, the whole thing. We don't have to do it one at a time because now we're not changing the what is considered an in and what is considered an out. Let's copy all of these, Control C, and then paste, Control V. All right. So, oops. The changes in F values are going to be more subtle now. 0.023, 0.022. So you can see that the velocities are pretty much from one to the other pretty much stabilized. So we can do maybe one last iteration just to make sure that we've got exactly the right F values. So I'm just going to delete all this oh, this is the updated one. Okay. I had an iteration 4. I'm going to create an iteration 4. In your template, is it just the third iteration and that's the end of it? Mm-hmm. All right. Let's add some more rows here. I want to do a 4th iteration. All right. So I'm going to copy everything. Control C. Here is Control V. I'm just going to rename this iteration 4. I'll do goal seek again to find we want it to be 0 by changing the guess of H sub D. All right. So 104.66, and it looks like the velocities are identical. The F values are identical. So now the solution is converged. So the conclusion is flow balance achieved. F values are stable. So the flow rates are as indicated. And then the process of calculating the pressure at junction D is just the same as in the example from Wednesday. We know the head at D, and we know the elevation at D is given as 85 feet. We'll calculate the velocity head in each of the pipes. So it is V squared divided by 2 times 32.2. So that's divided by 2G. So the velocity head in each of the pipes, then the average velocity head, because we're going to use that in this formula. If we rearrange that to calculate the pressure, then the pressure is the head at D minus the elevation at D minus the average velocity head, and then times the unit weight of water, which in traditional units is 62.37 pounds per cubic foot. So that gives us the pressure at D in terms of pounds per square foot, and if we want to know the pressure in terms of pounds per square inch, we would divide that by 144. So 8 psi is the pressure at the junction. So that would be more accurate to do the Darcy Weisbach equation because the F values are taking into account the flow conditions. And we've got one of these pipes with a velocity of 12 feet per second. That's a really high velocity. And another one with a pretty low velocity. So it's good that our F value is reflecting these unique flow conditions because our solution will be a lot more accurate that way compared to if we had just used some C value for cast iron and a different one for galvanized iron.